So this is problem 34 in your packet, 33 in mine. It says, in many applications, oppositely charged parallel plates are used to steer beams of electrical charged particles. In this example, we have a proton that's being injected into a space between plates. And it's being injected at a speed of 2 times 10 to the 6 meters per second. The plates have a known charge density, and the bottom plate is positive. The plates are 2 centimeters long, so they're not very long plates, and they want to know how does this affect the particle's velocity as it exits the plate. So the picture is similar to the one that we've looked at already with the suspended particle. We have these parallel plates. We know that the bottom is positive. We know that we have a proton coming flying, screaming in there. Because of the way the field will be set up between here, we know when it enters this region, it is going to immediately experience an upward force from the electric field, so it's going to come out steered upward. So it should exit the plates. It shouldn't hit any of the plates, but we know that's going to happen. And they want to know what's the position and the velocity. So we're back to looking at things in a kinematic sense as far as event 1 being enter and event 2 being exit. We know that there's going to be a whole lot of component work to look at. 2x, a1, 2y, and there's t1, so t2, r2x, r2y, v2x, v2y. So we know a lot of this is going to need to be filled in, and because I'm free to pick some things, I'm going to make all of this 0 as far as where it enters at position-wise, and my initial time. I'm also going to give it an initial 0 velocity, and as far as my x velocity, I know that's 2e to the 6th meters per second. I'm not going to give it any kind of x acceleration here because there's nothing accelerating it through the plates, but it is going to have a y acceleration from the electric field. So the way that I would find that then is Newton's second law tells me that there's an electric force. Technically I'd say minus the weight, but we're working with a proton here, and gravity doesn't really act on protons in any conceivable way. So I'm just going to say that's equal to ma. So this is going to end up being the electric force divided by the mass. And as we've seen, the electric force from parallel plates is just the charge times the charge density, and then over epsilon naught, and then times the mass. So the acceleration is going to be a known quantity to us. The velocity in the x direction, because everything's vectors, it's not going to speed up. There's no x acceleration. We know that it's going to pass through plates that are 2 centimeters long, so that's 2 centimeters. It's going to take a certain amount of time to do that. It's going to bend upward, and it's going to have some new y velocity. So we're going to have 3 equations and 3 unknowns after we determine what the acceleration is due to that electric field. So we can calculate that. They give us enough information, and everything else is just a constant. So what I'm going to do is I'm going to calculate everything at the end. And I'm just going to set this up so that I can find R2 and V2 and T2. And perhaps maybe the quickest way towards finding T2 is to take this relationship with R2x and look at it. So R2x is going to be equal to R1x plus V1x, T2 minus T1. And then remember, there's some more kinematics here. Mainly there's the piece that's 1/2 the acceleration times the difference in times squared. But so much of this is 0, including that acceleration in the x direction, that I'm just going to kind of drop it out. And we have this constant velocity relationship that looks like this. And those are all known quantities, so we can find T2. So T2 is simply going to be 0.02 meters divided by 2e to the 6th meters per second squared. And then we'll be able to plug that in. And then once we know T2, we're free to find V2y and R2y. So R2y, again, a lot of it's going to be 0. The initial position in the y direction 0. The initial velocity in the y direction 0. So it's just going to be 1/2 the acceleration in the y direction times that T2 value that we're going to find squared. So that's going to look a little bit more involved because it's going to be 1/2 q sigma over mass epsilon naught times T2 squared. And so you'll just plug that in and solve for it. And then lastly, V2y is going to be equal to the initial velocity in the y direction 0, so a12y, T2 minus T1, the T1 is 0, so we're just going to forget about it. So it's going to be q sigma m e epsilon, or m epsilon times T2. And it's just pretty straightforward. At this point, we plug numbers in and figure out what everything is. So let's do that. So running through these, you get a really high acceleration. It's 1.08 e to the 13th meters per second squared. Now this is only going to act for a brief time, as you find out when you do the calculation up here with the time. It comes out to be 1 times 10 to the negative 8 seconds, which is the same as writing 10 nanoseconds. Your other quantities then that you're trying to find, like your velocity, turns out to be 108 kilometers per second, or 1.08 times 10 to the 5th meters per second. So that's pretty fast, 108 kilometers per second. And lastly, the position where it comes out is 5.4 times 10 to the negative 4th meters, or 540 micrometers. So it only deviates slightly upward. That's that's like 1/2 of a millimeter of deviation that it moves up. So as long as it's these slits are more than a millimeter in difference, so at least 2 millimeters wide, if the particle enters in from the left side in the middle, it should just clear it just fine. So that's it. That's really all there is to it. It's primarily a kinematics problem after you realize that the acceleration is just this simple equation that we got from parallel plates. So the derivation of that electric field in the first place was, using Gauss's law. It required us to think. It required us to get rid of an integral, and it required some symmetry and things like that. But ultimately, having this for the electric field makes doing the electric force easy, and all this is really just algebra. So cool stuff with kinematics. You got some practice problems there in the homework, but that's it.